by Kevin Heng.
So thank you to the organizers for having me. I lead a new group at the University of Bern, where we spend our days thinking about the theory, simulation, and phenomenology of exoplanet atmospheres. But because Bern is also home to the CHEOPS mission, I spend some of my days thinking about optical data and what we might learn from it for exoplanet atmospheres. So that's the basis for which my story will be told today. It's a story told from a theoretician's point of view. So pardon me if some of it doesn't sound too observer-friendly. This is the agenda I want to go through. So I want to ask these three questions and try and address them, if not answer them. So what do optical data have to say about exoplanet atmospheres? That's the first thing you would ask. What trends do models and simulations predict? And what kind of improvements do we need to make in both observationally and theoretically in the future? So let's start with this schematic we all know and love. I don't need to explain to you how this probes the atmosphere. What I will say is that as we are going towards the era of TESS and CHEOPS and JWST, lots of different workers in the field are thinking about how to interpret spectra of exoplanet atmospheres. And there's a very nice paper by one of Sarah Seeger's students, Bjorn Benneker, where he basically laid out all of the different pieces of information that you can find in an exoplanet atmosphere spectrum. And specifically, I want to point your attention to the three boxes here. And basically, encoded in the spectrum is a way to figure out the mean molecular mass of the atmosphere, which gives you the main molecule in the atmosphere that makes up the bulk of the mass. On Earth is nitrogen, of course, and oxygen. So there are three ways to do this. The first way is to measure the shape of individual features, which requires that you have sufficient resolution in the infrared. The second way is to measure the relative strength of features of the same molecule. These are both challenging measurements to make. The third, and by far in principle the simplest way, is to just measure the optical Rayleigh slope below 1 micron, right here. So at least that's the hope. The theoretical hope is that if you measure this slope, you can figure out what the mean molecular weight of the atmosphere is. The big caveat is that this story is told for a cloud-free atmosphere. So what does the reality actually look like? So the reality is a little bit more complicated, because when you actually look at real transit spectra, it seems to suggest that many of these atmospheres are cloudy. So they are characterized, the best example is HD 189, and it seems to be characterized by a slope consistent with the presence of some kind of small condensate, small meaning radiatively small, and of some unknown chemistry. This seems to be the case for warps 12b as well, and it's less clear what's happening for HAT 1b. What is really puzzling, as the results are coming out from different groups in Exeter and Colorado, and John Michel is in the audience and can tell you more about this, as the results are coming out, is that it is unclear if cloudiness correlates with any quantity. Well, and now you must be thinking, so why do I care? And you should care, because if you want to back out chemical abundances and thermal profiles from these atmospheres, these are degenerate with cloudiness, just like you have learned for brown dwarfs, for example. So to back out these quantities with some degree of confidence, you need to understand cloudiness. Now, let's move on and talk about eclipses. So in optical light, at least, one of the nice things about measuring eclipses is that you can measure the amount of reflected light coming back at you from the atmosphere, the so-called albedo. Specifically, you're measuring the albedo at zero phase angle, known as the geometric albedo. But this comes with a caveat that the light you're measuring is mostly reflected light and not contaminated by thermal emission, something I'll talk about in the next slide. Why are albedos interesting? They're interesting because they give you the energy budget of the atmosphere, so how much energy actually enters your atmosphere. That's the most obvious point. A less obvious point is that about why albedos are interesting is because they affect the vertical profile of how energy is absorbed in the atmosphere, which affects things like how strong your molecular features are. So again, if you want to interpret atmospheres correctly, you care about this. And so together with my observer friend, Brice-Olivier Demory, we looked at a bunch of hot Jupiters from the Kepler dataset. And we looked at the secondary eclipses and just extracted the albedos as they were and plotted them against basically the incident stellar flux. And if you just stare at the blue points, your eyes seem to see a trend. But you have to be careful because for the very hottest hot Jupiters, the thermal emission is leaking into the Kepler bandpass. So your measurement is not just of reflected light, but also of thermal emission. You can correct for this effect. This correction depends on the amount of redistribution of heat from the day side to the night side, which is shown in the two different yellow and orange curves. It also depends on the albedo itself. And when you plot examples of these correction curves, you will notice that the yellow and the orange curves trend in the same way as the data. So when you correct for this thermal contamination, you get the circles that you can barely see. I apologize for that. So these circles are where the real measurements of the albedo should be. And when you do this correction, basically there's no obvious trend with stellar irradiation, which is very puzzling. So most hot Jupiters appear to have geometric albedos of roughly 10%, with this oddball, which I'll come back to in a few slides. So that's interesting because there are other trends in the literature, like for example, the inflated hot Jupiter problem. The radii do get larger with stellar irradiation. There's no trend here. So in a recent study that's on the archive, Daniel Engelhausen et al. Looked at this for a somewhat larger sample of objects, and they also looked at different trends with surface gravity and mass and radius and density and so on. And these different panels, as they are labeled, show you the mass, the radius, density, surface gravity. The size of the circles reflects the magnitude of the quantity. The size of the circles here reflect the magnitude of the surface gravity, and the color reflects the stellar metallicity, and there's no trend. And I'm not sure why. In a separate study, there was a trend, a tentative one, but an interesting one to think about. So just a few months ago, Brice Demory published a study where he looked at the geometric albedos of super Earths and hot Jupiters. And what he did was he measured the brightness temperature at secondary eclipse. Then he did the most conservative thing, which is he did the thermal contamination correction, which I tell you about, but he did the most conservative one that you could. So he subtracted the maximum amount that you could from this, and he plotted the excess in brightness temperature as a function of essentially the stellar irradiation flux. And what is interesting and tentative is that super Earths as a population tend to be slightly brighter than hot Jupiters. There's an observational bias here, which is that it's easier to measure brightness temperature differences that are small for hotter objects. So this issue is not closed yet. But it's interesting that this trend even comes out. And the reasons for it would start going into the realm of speculation. So are the atmospheres fundamentally different? Are you looking at vapor atmospheres? Are you looking at surfaces? So it's not clear, but more data in the future would be interesting to address this question. For the case of, for very optimistic cases, such as HD 189.733b, you can actually measure using HST the albedo spectrum. And this is work by Tom Evans et al. At Oxford, where in the paper itself, they presented both 2 channels and 6. So I'm showing the 6-channel result plotted. So it's the geometric albedo spectrum plotted against wavelength. And there are 3 possible interpretations of such a result. So the interpretation which was presented in the paper, which I show in color in blue and in the panel, is Rayleigh scattering by condensates of unknown chemistry. You can specify the refractive index, but that doesn't always tell you what the composition is because it's weakly dependent on the composition. And absorption by sodium atoms, which have been observed in HT189 in transit. So when you do this, you realize that the theoretical albedo spectrum is extremely sensitive to the size of the scatterers because the Rayleigh scattering cross-section goes as the 6th power of the radius. So if you know what the sodium abundance is, you could figure out the size of the scatterers, which you will see towards the end of my talk is what is the most important parameter to understanding and breaking the degeneracies due to clouds. Another interpretation is that it could be Rayleigh scattering by hydrogen molecules and absorption by sodium atoms, which require much less sodium to be present. A third interpretation is that you could have no sodium at all. You could just have silicate carbide grains, 10 nanometers to be exact, and it would also give you roughly this shape. So it's degenerate, and again, it will be interesting to see more data on different objects. So staying on this subject, there was a nice study in 2010 by Cahoy et al., where they did many things in the paper, but one of the things they did, which was interesting, is they took data from the solar system and rebinned it, optical data, and rebinned it at very coarse spectral resolution, so R equals to 5 in this example. And the point of this figure is to tell you that even with very coarse optical spectra, you could potentially distinguish between the ice and the gas giants. So even limited optical data would tell you something about the atmospheres of planets. So moving on, let's talk about phase curves a little. And I think they are really underappreciated in the literature. So phase curves measure the reflectivity of the exoplanet atmospheres and therefore the relative abundance of clouds if they are present. And the example that I will show is nice work by Brice-Demory again in 2013, where he measured, you can see the eclipse and the transit. From a theoretical point of view, what's interesting about this phase curve is that it peaks after secondary eclipse. As far as I'm aware of, and people can correct me, all of the infrared phase curves peak before secondary eclipse. The very interesting theoretical question here is if the phase curves in the infrared, which traces the thermal emission, and the phase curve in the optical, which traces reflected light, coincide and trace each other. This wasn't clear. We tried to get thermal phase curves using Worm-Spitzer, but we only got upper limits, I believe. And so this question is open, but a very robust indication that clouds are present in the atmosphere is if you get both optical and infrared phase curves, and you look at how reflected light and thermal emission are varying across the longitude of the planet. So what do the observations tell us? So the transmission spectra are suggesting that some exoplanet atmospheres are cloudy, for others are not. The reasons are currently unclear or unknown. Measurements of the geometric albedo seem to indicate that there's no clear correlation with any property of the exoplanet. Super-Earths appear to be more reflective than hot Jupiters as a population. Why? And why we care? Because, as I mentioned earlier, if you want to back out abundances and thermal profiles, say from JWST spectra, you should care. And towards the end, I will show you one example of this degeneracy. Now, the next thing I want to address is what do simple models and scaling laws predict? So in the panel, I'm plotting something called the Stokes number. The Stokes number is the vertical velocity of the flow in the atmosphere divided by the terminal velocity of the particle, such that if this number is greater than 1, you expect the particle to be lofted in the atmosphere. The Stokes number has different regimes determined by something called the Knudsen number. The Knudsen number is a correction for non-fluid behavior in the atmosphere. It's not so interesting to explain it in detail, but most particles that you come across in typical pressure levels of an atmosphere will have Knudsen numbers much greater than 1. And in this limit, the Stokes number scales just as the pressure of the layer in which most of the starlight is going to land in the atmosphere. So now if this pressure at which the starlight is being deposited, which is the opacity effect, doesn't depend strongly on stellar irradiation, then you expect the Stokes number to be flat with stellar irradiation, which is consistent with what you see in the observations. So for different particle sizes, 1 micron particles are very easily lofted in the atmosphere, also consistent with what simulations find, as our next speaker will tell you. 10 micron particles are partially lofted up as a population, and it's pretty hard to loft 100 micron particles. The different trends you see with the different albedos comes from the fact that when you change the albedo of an atmosphere, you are probing different pressure levels in the atmosphere, and therefore P is changing. And that's the effect you're seeing. What do 3D general... Sorry, I'm not done with this. So here are some suggestions, I would say, for what simple models and scaling laws would predict. If you go out and measure a sinusoidal optical phase curve, this would suggest the presence of large cloud particles. If you measure a flat phase curve, this would indicate small cloud particles. If you measure a high albedo and a small infrared offset in the phase curve, this is expected from the high albedo leading you to sample the atmosphere at higher altitudes. If you measure a low albedo and a small infrared offset, this is expected for highly irradiated objects. And the point of this is that these are a bunch of falsifiable scenarios. You can go out, you can measure, you can prove them wrong, and you prove them wrong, we hope that we learn something. So next, what do 3D GCMs predict? So this body of work is in its early stages, and the first study on this is a study by our next speaker, Vivian Parmentier, so he can tell you more about this than I can. But what they did was they put tracers in 3D, essentially a climate simulator, and tried to understand what clouds are, how clouds are interacting with the flow. There are tracers in the sense that the flow acts upon the particles, but the particles have no radiative feedback on the flow. And you know from the urgency of climate change on Earth that this is not the case for particles. Well, but the trends they predict make a lot of sense. So it's very easy to loft small particles. So you should expect that submicron and micron particles should be ubiquitous in exoplanet atmospheres. It should be very easy to keep them at the pressure levels where you probe them with transits. Because the flow of the atmosphere is expected to decrease as you go up in altitude, you expect the abundances of cloud particles to drop off, and this is what the simulations predict. And the simulations also predict that the tracer abundances should vary with temperature and longitude and latitude. And this is interesting because you can potentially probe these structures with optical phase curves. So now let's, related to 3D GCMs, let's go into a topic that's a little bit more controversial. And this would be the measurement of 2D maps using a technique called Eclipse Mapping. It's controversial because, well, let's talk about conceptually what it is first before I say it's controversial. So you can measure infrared data of your regular phase curve, which gives you east-west information if the spin axis is aligned with the star. Now, if you have high cadence at ingress and egress, in principle, as this cartoon suggests, you would have north-south and east-west information, and in principle, you could combine these two data sets and back out something like a 2D map. Why is it controversial? Because the backing out of the information depends on the precision to which you measure several orbital parameters. So you could get multiple solutions if your error bars are large. But the question I want to pose to the audience is that do we dare think about doing this in the optical? Because it would be very interesting. For example, you could ask the question of if hot Jupiter clouds are patchy, which is what we find in brown dwarfs. And that would go a long way towards interpreting future spectra by JWST. So to start to end, I'm not ending yet, what observations do we need for the future? I would say it would be interesting to get a larger sample of optical eclipses So specifically measure decontaminated geometric albedos for not just hot Jupiters, but Neptunes and Earths across a range of different exoplanet properties and stellar properties. That will be really interesting to look at to see if there are any trends. We need to recognize the value of optical phase curves. I think they haven't been so appreciated in the community. And there will be a talk, I believe, on Wednesday by Ray J, where he will talk about this more. It's important to measure both optical and infrared phase curves, as I mentioned, because then you get a handle on both the thermal profile and the profile of reflected light. And this is more than twice the value you will get. And the speculative scenario is, could we do eclipse mapping in the optical? I don't know. Some observer should tell me if it's possible. What models do we need to construct for the future? So the study of clouds has a long, I would say, torturous history in many parts of astronomy. And we need simple, clear, phenomenological cloud models with a small number of parameters so that we can put them into retrieval codes and GCMs and so forth. Having said that, we should have also more realistic clouds in GCMs, meaning that the clouds and the flow should feed back on each other, both dynamically and radiatively. We also need to couple the microphysics better to the large-scale flow and stop interpreting spectra with 1D models. And we need to understand what we can actually learn from optical phase curves. Now, after this preachy part, here's an example where I show you the degeneracies. So this is HD189 using the unified data set by Pond et al. In 2013. And that's the data, as you see. And these are different interpretations of this data set using a technique known as retrieval, which I don't have time to explain, but essentially it's an inverse technique that goes from the data to atmospheric abundances and thermal profiles, and it reports a chi-square, right? So what we did was we took a very simple approach. We said, on top of the retrieval technique, let's add a cloud model with two parameters. So we pretend that the cloud has particles all have the same size. They're uniform throughout the atmosphere, and they can be described by an optical depth. So here are different solutions. And notice that these solutions, while the Rayleigh slope in the optical tells you that small cloud particles are present, the different solutions with slightly different sizes are degenerate all the way up to 8 microns. So in fact, this single point, MIPS point at 24 microns, is more constraining than all of these other points. It's actually breaking the degeneracy because the extinction efficiency is changing as a function of wavelength for different particle sizes. So the take-home message is that we need optical data to tell us that clouds are present, and we need data above 8 microns to completely break the degeneracy due to clouds. I'm not showing you this here, but the atmospheric chemical abundances for each of these solutions are rather different by factors of 2 or 3 or more. So you really want to understand this. So let me conclude. I think the utility of using optical data for studying exoplanet atmospheres has been demonstrated. In some ways less, in some ways more. But its full potential has yet to be realized. So we should measure more secondary eclipses, phase curves, and do eclipse mapping. Judicious combination of optical and infrared data in the future will break the degeneracies due to clouds for interpreting spectra of transiting exoplanets. And in the abstract, I promised you that I would address this question in my third point. But as I started digging and investigating, I found that the answer was in flux. So instead of answering or addressing the question for you, I'm going to pose it to the audience, which is, how will these scientific goals be realized within the observing strategies of TESS, CHEOPS, and Plato? And with that, thank you for your time. Thank you.
First was Juan at the far end, then for more of that.
You talk about this phase curve of super Earths. I think there is one page, I talk from memory, so maybe I say something wrong, sorry for that. It's 55 Cancri E was observed by the MOST team, and they see the phase curve of the planet, but then they see an amplitude that depends on time. and which is far too large to be explained only by reflection on the planet. So they think that there's something going on the star that is also masking the signal that we get from the planet. Do you know how could we disentangle these two signals to do the measurements from the planet?
I remember the paper. I don't remember all the details, but I think the difficulty with that planet is that it's sufficiently hot that you worry about thermal contamination as well. So you have a number of things to disentangle. So I don't know. I don't have a clear answer for that.
Okay, next.
I like that you say that we have to combine optical and infrared data. And so the most obvious optical data set is the Kepler data set. Unfortunately, isn't it true that all of those objects are too faint to measure in infrared in any way? I mean, Kepler 7 is probably the best target you have, and even there you can only get upper limits with Spitzer. So we don't have any usable Kepler targets to do infrared observations for.
I don't disagree with anything you said, and hence my third question.
There's a blue-white t-shirt with squares. Blue-white shirt. Yeah. Okay, there was one more back here, yeah. And who else was then afterwards? Okay, Jamie.
So Kevin, we see a large diversity of albedo for Jupiters, like from 0.3 to 0.03 for trace 2b. What's your explanation about this diversity of albedo, and how can you explain such a low albedo for trace 2b?
So in the paper I wrote with Brice-Olivier Demory, we basically consider a bunch of scaling laws, that some of which I presented to you. And the basic conclusion was that there were, even though the parameters that you could change were small, 3 or 4, you could change them sufficiently enough that it would wash out any trend. Is my pessimistic answer to your question.
Okay.
Two questions. One, to respond to the 55 Cancri-E point. One of the advantages of the most bandpass compared to Kepler and CoRoT is that it doesn't admit any thermal emission. It doesn't admit any thermal emission. So our eclipse measurements are a true optical albedo measure. So in the case of what we see with in the 55 Cancri-E data, at least the modulation we see, there is no contribution from thermal emission. We've done the calculations for backheating and so on, and that can't be an explanation. On a similar note, for HD 189733, our eclipse measurements combined with the published Spitzer infrared data are very compelling to indicate that we're seeing Rayleigh scattering in the atmosphere of that planet.
Thank you for those comments. I stand corrected.
Kevin, maybe I missed it, but is there a simple explanation for Kepler 7b? Simple explanation for why the phase could peak after the secondary eclipse. Is there a simple way to?
The short answer is no, and we said that in the paper too.
Okay.
It's
so
puzzling.
What's degree? What degree? How many? How much phase lag? What's the 20 degrees or 30 degrees?
It must be of that order because it's big enough to actually see it.
See by eye, yes.
Right.
I see. It's very interesting.
Yes, Kevin, you asked a question about whether you should have, for example, the same, if you see the shift of the hotspot with the brightness temperature, so which means very high in the atmosphere, whether this should reflect also what's happening if you look at the same phase curve in the near infrared. But actually I do not expect at all to have any correlation, because one side you see very high atmospheric winds, on the other side you see kind of deeper winds. They may be totally decorrelated. So I'm not sure this can, tell us something about, I don't know, really the correlation or dynamics of the atmosphere, whether the winds are in the same direction or not, or so what do you think about that?
I think my reading of your comment is a bit less pessimistic. So the optical data probes the optical photosphere, actually the photon deposition layer. They're not quite the same thing. And there's no reason that the photon deposition layer should coincide with any of the infrared photospheres. So I would read it as, if I have optical data and infrared data, I'm probing two different layers of the atmosphere, which gives me extra information to confront my model. Thank you. Thanks for having me.